All right, so let's move forward. So, so that was like a very simple extension of classification to solve detection. Now let's move on to like the first CNN based approach, which was proposed for object detection. Okay, so this is like a real algorithm, and this is one of, I will say, like one of the breakthrough in object detection, and it has won like several awards as well. And even like many methods which are developed today are actually based on this idea, and very simple idea, right? Now, and again, this is like what Mohammed just asked: what if we have multiple instances? Okay, so right now what we are doing is we are solving detection as a regression, right? So we might have multiple objects in the image. And in this case, like if you look at this image, we have a dog, we have like two different cats, right? And we have a duck. So if we have to solve this, we have to train a network for this. The regression task will be like these numbers. So these are like bounding boxes for each of these instances. And here you can see that you have two different instances of cat. So in total, these are 16 numbers. Now, if you look carefully, the earlier algorithm which we discussed, we had like C different predictions, right? For each, for C different classes. But in this case, for each class, for example, cat, we might have two instances. So, but we don't have that in the prediction, and that's the issue. This kind of simple approach will not take into account multiple instances which could be present in your image. Okay, so that's one issue. The second issue is, for this particular instance, you need 16 numbers because you have four different objects, right? Irrespective of which category. In this image, you only have two objects. So this will require just 8 numbers. Now, the issue is you know by now that when you are training your model, the network's prediction, it's not flexible. Okay, so if you have 1,000 classes to train on, you will always have to train for 1,000 classes. You can't say that, okay, this time I will train for 100 classes. This time I will train for 100,000 classes. It doesn't work that way because your network architecture is fixed and the whole training process is kind of fixed, right? Probably one day we'll come up with architectures which are kind of flexible, but we don't have that today, okay? So the issue is with detection, we need something where like the output is actually varying a lot. It's not just having multiple instances for each object category, but also having like multiple objects itself, okay? So one simple solution to this problem could be, again, if you go back like what we discussed earlier, sliding window was very interesting approach, right? And we can try to solve your detection problem as classification problem, and that's exactly what we saw when we're trying to do sliding window. And the idea here is you take a bounding box and you say that, okay, if any particular object category is present or not. In this case, if this is a bounding box, cat is no, dog is no. You slide it, cat is yes, dog is no, right? So this is a classification problem now. And what we are classifying, we are trying to classify the features which you are getting from this bounding box. And this is like in very much alignment with the first algorithm which we studied for object detection, which was completely sliding window, right? Okay, so that's like exactly sliding window. Now, let's try to understand what are the issues with this algorithm. So first of all, we have to test like each and every possible location. And if the resolution of image will increase, those locations will increase. So there is some scalability issue. And not just position, you also have to test different scales so that your algorithm is scale invariant, right? So which further which further like increases the computational complexity. Okay, so different scales, you have to search different positions. Now, this algorithm, and again, you will be surprised like the solution they have. You only have to look at like only subset of possible solutions. And that was the solution. Exactly, that was the solution. You don't look at all the possible locations, but look at only a few set of locations, and it will solve the issue of this scalability. And that's what faster RCNN actually did. Not faster, the RCNN actually did, the first version of that algorithm. Okay, so let's see how that can be done. So the basic idea was coming up with this region proposals. And again, this is something which we have like discussed a lot in this course, how to find like the interesting points. SIFT used to do that, right? And we have like many other algorithms to do that. I think we also studied corner detection, Harris corner detection, that also gives you the salient points in your image. So that was the whole idea. What if we don't scan all the possible locations, all the possible scales, but we use some algorithm to actually subsample this space for us? For example, if this is your input image, we will run that algorithm, and that algorithm will tell you, okay, these are the places which are like most likely where objects are present. Okay, and it will also give you some kind of scale as well. So now if you think about this, in this scenario, you have like a lot of different scales, right? The smaller bounding box, you have the bigger bounding box. Some of these bounding boxes are actually perfectly covering the objects, cat and dog. Some of these are covering the flowers, some of like the nose, the eyes. So we have a lot of variations. But if you count these are just like handful, maybe 10, 12, or 15 different bounding boxes. As opposed to if you have used like all these scales, then if you have slided those variations in this input image, that would have given you thousands of locations and variations. Okay, so that's the crux of this first algorithm. You subsample your search space. And of course, there are a lot of algorithms to do that. And in their work, I think the first work, they used this selective search algorithm. And again, we don't have to go through like the detail of this algorithm. The idea was just like to select key points, which will give you these region proposals. So these are called region proposals. And the architecture was called region proposal network because it was utilizing these region proposals. Now, I think this, we can quickly go over this. The idea was you perform some kind of segmentation, and we're going to talk about segmentation later in the course as well. So don't worry about how this can be obtained. We'll cover some algorithms for that as well. But the idea is it tries to group like pixels together for similar objects, right? And again, we can do that at multiple scales. This is looking at fine level details. Again, this is coarse level, and this is even coarser. And once you do that, then you can convert these regions, or you can say like superpixels or segments, into these kind of proposals. So then what you have in the bottom, these are your region proposals, and you will only look at these possible locations. Okay, so this reduces like the computational complexity a lot. Now let's try to understand how that can be used in this deep learning kind of architecture. And of course, there are some limitations which we'll cover later on. So this architecture is called RCNN, and R is for region proposal network, and CNN is for convolutional neural network. And CNN is because we are using like features which are extracted by CNN architecture, and R is like we are using subsampled region proposals. Now, what we do is, given an input image, we first run that pre-processing algorithm, which will give you these region proposals. Okay, it will give you like all the bounding boxes, possible locations with different scales, varying scales. Now, what you do is for each bounding box, you will actually try to warp that image. So what you will do, you will actually make sure that you reshape all the proposals into same resolution. And you can, that's a parameter of the architecture. You can say, let's say this is 28 cross 28. So all the region proposals will be reshaped to 28 cross 28. Doesn't matter like what was the original size. Okay. And I think roughly the idea is to use around 2000 proposals, which is again not very small number, but again not very huge number. But it covers like most of the variations you can have in your input images. And again, that's like one parameter which you can change. You can try like fewer proposals as well. You can try more proposals as well, depending upon like what kind of images you have in your data set. Okay, so that's the first step. You resize them. And once you have resized, then you have your CNN architecture. And you know that CNN architecture takes like images of fixed size, and now you have make them like of fixed size. So you pass them to the CNNs and you will get the features. Okay, so once you have the features, you train your classifiers on those features. And in this case, the classifier which was used was support vector machine. And we have discussed support vector machine, right? The input to support vector machine is some set of features, and you train it for classification. Now, let's see how this kind of approach can solve detection and classification simultaneously. Given an image, you will have lots of proposals. Everything will be resized to the same resolution, passed to the CNN, and that CNN will give you features which you will pass to a SVM, which is a classifier, and that classifier is going to give you which class is present. And it's also going to give you some kind of adjustment to the bounding box. Okay, so this second prediction is corresponding to the location of your object. Now I will explain like why exactly we need this bounding box regression. But before that, let's first try to understand like how this is working. Now we talked about sliding window algorithm, right? And we talked about like converting detection to classification problem. And this is exactly doing that, because you are looking at like a very smaller crop of the image, and you're just classifying whether in this crop this object is present or not. For example, if you have 1,000 different categories, this SVM is going to classify like those 1,000 categories. Okay, so this becomes classification problem. So now you know that what object is present in this particular region, and in this in a way it's actually also giving you the location. Okay, but in reality what happens is this location is not perfect. You might need some kind of adjustment to it, maybe rescaling the bounding box or moving it slightly, some adjustments, right, to make it more perfect. And to do that, we need this bounding box regression. And this prediction is just telling you, given the location of this bounding box in the input image, how should I adjust those points so that the prediction is actually better aligned with the ground truth. And again, you have the ground truth, so you can compute that loss. Okay, so you do that for all the patches here, all the 2,000 patches. And that's how you solve your object detection problem using some, you can say it's not completely deep learning, but in a CNN way. And that was the first algorithm, and it worked really well. Okay, so regions roughly 2,000, as I said. And so as a backbone, I think AlexNet was used because that was the architecture which was available at that time. And it was pre-trained on ImageNet dataset where we have 1,000 different classes. And like ImageNet at that time, it was just for classification. So later it had to fine tune with Pascal VOC, which is object detection dataset. Okay, so these are some statistics of that architecture. We can quickly go with these. Yeah, so this step is fine. You resize your patches. And FC7 is just like one layer of your AlexNet, right? If you remember from one of the lecture. And the number of neurons in this layer was 4096. Again, that's just a stat. And you use this as input to your SVM, which is going to give the classification, which class is present actually in each of these patches. Okay. Now quickly go over like the steps, like you try to understand like how cumbersome this was. The first step was you have to get like this pre-trained model, these weights, right, which was trained for classification. And then the second step was you will have to create like a new layer, because imagine it was 1,000 classes, but your target data set, let's say, which is VOC, there were I think only 20 classes. So you will have to change that. And again, these are just technical details. And then I think this was pretty huge thing back then. You had to extract features actually for all the region proposals, and you have to save them on disk. Okay, it was a different world back then. So for all the proposals, like you have roughly 2,000 proposals for each image. So you resize them, you pass them to the pre-trained network, you extract the features, and you save to disk. So for Pascal VOC, it was roughly 200. In these days, 200 gigabytes, it's not a lot, but back then it was a big deal. Okay, so once you have those training features, then again, this is the same process what we discussed for the sliding window approach. Now, each batch, you have the feature and you have the ground truth of the detection, right? So you can say that, okay, this is the true class or not. For example, if you're looking for cat, then these are the positive samples. Then you will also mine some negative samples. This is not a cat, not a cat, not a cat, right? And what you do is for each class, you train a binary SVM. So if you have 1,000 different classes, 1,000 different SVMs, VOC has 20 different classes, so 20 different SVMs. Again, which is kind of cumbersome, not that trivial. Okay, so this will be like the training data, which will look like something like for dog. This is the positive sample and all these will be negative. Now, so that was for classification. Now let's quickly look into like how regression adjustments were made. Now your region proposal will give you the bounding box, right? Something like this. And if that bounding box is perfectly aligned with your ground truth, then your proposal is pretty good. So what you will predict is 0, because you don't need any adjustment. Okay, but it might be something like this, not completely aligning with your ground truth. You need some kind of adjustment. And again, this adjustment, like it's up to you, like what you want to predict, right? Because you have the bounding box for the proposal, you have the bounding box for the ground truth. It's up to you how you want to align them. And this is just one way. And I think what this is trying to do is 0.25. So this, I think, is just saying that you shift your X coordinate to the right by this much amount, 0.25 amount. Okay, then it will perfectly fit. Okay, so it's slide towards right. But again, that's just one way to do the adjustment. You can have like many other variations here as well. In this one, I think it's saying negative of this. Of course, we have it here, right? Okay, so in this case, what it's showing is, so we have 4 different numbers for adjustment, right? And the first number is how much should you shift your X value, right? So this is 0.25, so you will shift X to 0.25. And the Y is telling you like how much you should shift in the Y direction. And the W and the H is like how much you should change your height and width. So these 4 combinations actually cover all the adjustments you might need. For example, in this case, it's negative. So it's saying that your bounding box is actually too wide. Make it a little thinner by that much amount, and then it will fit perfectly to your ground truth bounding box. Okay, so the second prediction, which was the bounding box regression head, you will have predictions like this.